Hello and welcome back to Calculus 1 section 4.4 on graphing functions by hand. Graphing functions by calculating a whole bunch of stuff from calculus and then algebra and pre-calc obviously, and then working it out. I'll stay. So for this to happen, what I do is I first go through the shopping list of all things needed. Call it a shopping list. Number 1, domain. Number 2, X and Y intercepts. Number 3, vertical asymptote. Number 4, horizontal asymptote. Number 5, slant asymptote. Number 6, first and second derivatives. Number 7, first derivative test to give us increase, decrease, plus, min, max. We know that we get that for free. Number 8, second derivative test to give us concavity. Number 9, we can also look at symmetry. It's not important, but we can. 10, and behavior. 11, additional points. And number 12, graph, finally. Now, these 3 only if needed. Or, you know what, as needed. That's better. As needed. As needed. There we go. Much better. As needed. And the reason for it is usually you have enough information from 1 through 8 to graph the function, and any additional information would be overkill. But in some cases you don't get enough stuff from 1 through 8, and then you have to go and work on additional points or additional stuff from there. So let's take a look at this. Can this be used to graph x squared? Sure. X cubed? Sure. Square root of x? Yep. But those are basic functions. You should know what they look like. What we want to take a look are functions that we don't know what the graph looks like when you look at the function, like y equals 3 square root of x minus x to the 3 halves. What's the graph for this? Something, exactly. That's the best answer we can give now. Something. So let's go and take a look at the something. So where do we begin? Domain. So if we look at the function, what is the domain of square root of x? Zero to infinity, great. And this is, you have an over 2, so this is technically square root of x cubed. So it would have the same domain, right? Because you still have square root of x. So domain is 0 included to positive infinity. Do we have X-intercept? And how do we calculate X-intercept? Set y equal to 0. So this is from algebra. When we set y equal to 0, we have 0 is equal to 3 root x minus, I'll put root x cubed. So now this is going to be 0 is equal to 3 root x minus x root x, because you have root x times root x times root x, right? These two make an x. So x root x. And now we factor out root x. And we have 3 minus x. So root x equal to 0. And 3 minus x equal to 0. X equals 0. X equals 3. We have 0, 0. And 3, 0 as our x-intercepts. Y-intercept, we set x equal to 0. Well, we're just going to get 0, 0. Anytime you get 0, 0 for x-intercept, it has to be a y-intercept, because that's the only point that it's both at the same time. It lies on both axes, the origin. The next one is vertical asymptote. Do we have any? Is there a vertical asymptote for square root of x? No. How about horizontal asymptote? So, none? Yes, there's none. And slant asymptote, obviously it's none. You can only have slant asymptote in one case. So no asymptotes of any kind. Great. What's the first derivative, f prime? Well, our function is 3 root x minus x to the 3 halves. So what's the derivative? It's 3 over 2 root x. The derivative of square root is 1 over 2 square root of x. And then you have times 3. Minus 3 halves x to the 1 half. So we can actually call that square root of x to be consistent. So this would be our first derivative. Now, actually we can simplify it a little bit nicer to get 3 halves, and then you get 1 over root x minus root x. Nicer. Now we want the second derivative. And for the second derivative, you take the derivative of the first derivative. Now, usually it's easier if we just have all of these written as, these written as x to the negative 1 half minus x to the positive 1 half. Right, that's what it is. So now when you're taking derivative, you copy 3/2, and then you just take derivative of each one of these. So derivative of x, it's a negative 1/2, x to the negative 3/2, minus, and then this is just 1 over 2 root x because it's square root. Okay, good. So now we can kick 2 outside. F double prime of x becomes 3/4. And inside we have 1 over x to the 3/2 minus 1 over square root of x. The 2's went out. Ooh, and there's a negative. So I'll kick the negative outside as well because both terms were negative. So kick negative outside and it becomes a positive in here. So I have my two derivatives simplified. Here's the first one and here's the second one. Now we do first derivative test. This is what we did last time. First derivative test is we take our 3/2, 1 over square root of x minus square root of x, and set that equal to 0 to find critical points, which turn into min and max. Three halves has nothing to do with anything, so if we multiply both sides by 2/3, the problem stays unchanged. So what do I do with this equation now? 1 over square root of x minus root x equals 0. I need to solve this equation. What should we do? Other than cry. We could. Yeah, I can, but it's much easier if we move root x to the other side and then cross multiply. We get 1 equals to x. So if x is 1, this thing works. All right, so now we have to partition. Partition is going to start at 0 and go to infinity. We only partition at 1, and that's 0. So we only have from 0 on because of the domain. We don't care about negative x values here because domain is 0 to positive infinity. Pick 2 test points. These are all calculations we did yesterday. Actually, maybe better test points here would be a 1/4 and a 4, because we have to take some square roots. Yes.
Probably stupid, but why don't you put in 0 as a test point?
Well, you can't because it's at the edge.
Oh, okay, never mind.
It has to be in something from the region inside.
Okay.
Right, so you can pick any number, but you can't pick those. And so now, f prime computed at 1/4 is going to be 3/2 times 1 over square root of 1/4 minus the square root of 1/4. That's 3/2. Square root of 1/4 is 1/2, and it goes up, it becomes 2 minus 1/2. There we go. And as I said, we don't even care what the number it is. We know it's bigger than 0. So we have an increase over here. For our second test point, which is 4, we plug everything in. 1 over square root of 4 minus square root of 4. That's 3/2, no coughing. 1/2 minus 2. Now that's going to be less than 0 because 1/2 minus 2 is negative. And what we found is that at x equals to 1, we have a maximum. Because the arrows go up and then they go down. So we have, yep, that's what we have. Now, we did first derivative test, and we can say that f of x is increasing on 0 to 1 and decreasing on 1 to infinity. Now I am using a square bracket here for 0 because that was provided in a problem. Second derivative test, same thing. Same procedure, same steps as first derivative test, except we use the second derivative function. So second derivative is negative 3/4. And then we have 1 over x to the 3/2 plus 1 over root x. Set it equal to 0. We have to solve 1 over x to the 3/2 plus 1 over root x equal to 0 because, right, when you multiply both sides by 4/3, it goes away. So now we do the same trick. We ship negative 1 over root x to the right hand side, and then we cross multiply to find that square root of x is equal to negative x to the 3/2. Now, as I said before, negative x to the 3/2 is negative x root x. Good one. So now we solve, move everything to the same side, factor out root x, and we get x equals 0, which we can't use, and we get x equal negative 1. Also can't use, not in the domain. Our domain is 0 to infinity, and we got the inflection points to be at negative 1. Well, that's not in a domain, so we don't have to worry about it. So what do? The entire 0 to infinity is one partition. So pick a test point, say 1, and then run that in the second derivative. So negative 3/4, 1 over x to the 3/2, 1 over square root of x. Was it plus or minus? Plus. And replace all of these x's with negative 1. No, with a positive 1, sorry. So what we have is negative 3/4, and you have times 2, that's less than 0, so the whole thing is concave down. Now, we had one maximum point, so of course it's going to be concave down, because concave down has a maximum point on top, right? So that's what we have. So concave down because second derivative was less than 0. So now, when we are done with all of this, we can finally graph our function, because we have a lot of stuff on a pile, right? So when we draw the graph over here, remember that domain starts at 0, so we don't have to worry about stuff to the left. They said that there is a 0, 0 y-intercept. Perfect. and x and y intercept was at 0, 0. Another one was 3, 0. So these are my x-intercepts at 0 and 3. And then we have a max at x equals to 1. But I never computed the y value for 1. So our original problem is square root of x, 3 times square root of x minus x to the 3 halves. So this is equal to 2. Okay, great. So 1, 2. I have to use some magic over here. So I plotted, maybe I should use red to plot all of the important points. And now all we need to do is to connect these so that it will go up to hit the maximum, and then we'll turn down and pass through x. And it has to keep falling forever because it's concave down. That's one. And there are no minimum points to bounce up. There are no vertical asymptotes to bounce over. So all of these things that would nudge the function to kind of turn, none of those things are here. So now we live in great times when you can go and just graph your problem and see if it matches the graph you came up with your calculations. So 3 square root of x minus x raised to open parenthesis 3 halves is 1.5. I don't need the parenthesis. Oh, it's fine. Oh, look at that!
You can't see it.
Look at that! What do you mean you can't see it? So 0, 0 x-intercept, y-intercept, 3, 0 x-intercept, 1, 2 the max that we calculated, increasing up to 1, decreasing after that, and always concave down. Cool, huh? Yes, what's the question?
Why did you use only one test point for the second derivative test?
Because there were no partitions. There were no vertical asymptotes and no inflection points. So there was nothing to partition with, so entire domain is one partition. If I had one inflection point, right? If I had one vertical asymptote or something like that, but I had nothing. So you can pick any point you want under the sun, which is obviously in the domain. It has to be in the domain.
And then during the first derivative test, we wrote f of x is increasing on 0 to 1, and there's a closed bracket on 0. And
Because there was given in a domain.
Right, but isn't 1 in the domain? And that you did 1 to infinity.
Yeah, but 1 to infinity because the other one closed at 1. So you can't have 1 to be for increase and 1. And we also don't use single points there because function cannot be increasing or decreasing at one point. Right? You have to have at least another point so you can compare which one has a higher y, so you can call it increase or decrease. Good. Look at the problems. Any takers?
Bottom of 30.
3, 0? Okay. Well, I just got excited and then just killed it.
Maybe we do a simpler one.
30 is perfect. It's amazing. Let's talk about problem 30. By the way, we're not learning anything new. We just took a whole bunch of stuff you know from before and shoved it all in one procedure to graph a function. We did not learn new type of a derivative. We did not learn nothing new. So problem 30, it says y equals 2x minus 3 divided by 2x minus 8. We're going to run through the whole spiel and see what we get. So domain. Wrong.
Oh, it can equal.
It can equal 4, exactly. So you have to kick 4 out, because if you use 4, you get 0 in denominator and the whole thing explodes. So 2x minus 8 equals to 4. Equals to, 0. From where x is equal to 4. So that's the bad point. Bad point. There we go. So what you do is, since that's a bad point, you go and you write domain from negative infinity to 4, union 4 to positive infinity. So that's my domain. Okay, X-intercept, we set y to 0. That means 2x minus 3 over 2x minus 8 equal to 0. And when you cross multiply, all you get is 2x minus 3 equal to 0. X equals 3/2. So X-intercept point is at 3/2 and 0. That's 3/2 is like 1.5, so not a big deal. Y-intercept, we set x equal to 0. And plug all of those. So when x is equal to 0, we have 2 times 0 minus 3 divided by 2 times 0 minus 8, which is just negative 3 over negative 8, which is 3/8. So 0 and 3/8. And that's the y-intercept. So we did domain, that's algebra. We did x and y-intercept, also algebra. And now we do some pre-calculus/calculus with asymptotes. Do we have a vertical asymptote? Do we have a vertical asymptote? At 4. Good. X equals 4. Vertical asymptotes are at the same time interruptions in your domain. So vertical asymptote and domain have the same calculation. If there are any ambiguities, you use the limit. How about horizontal asymptote? Do we have horizontal asymptote? What? Y equals 1. Nice. There are 2 ways to end up. If you have that one, you can't have slant because they're mutually exclusive, the slant asymptote and the horizontal asymptote. So now, horizontal asymptote, you can get this in few different ways. If you memorized, because these are polynomials, if you memorize the rule in pre-calc, it says to look in the highest power, both numerator and denominator, and if those terms with highest power have the same exponent, then we just look at the ratio of their coefficients. So the highest exponent x is 1, and on the bottom also 1. So we look at their 2 divided by 2, and we get 1. So we have now 2 asymptotes. We did not have this last time. It is time for us to enjoy the first derivative. Well, that's a quotient rule. 2x minus 8 squared, 2x minus 8, and then 2, and then minus 2x minus 3, and then a 2. Now we need to simplify this mess because we will be using it actually. If I factor 2, what's left is 2x minus 8 minus 2x plus 3, and then 2x minus 8 squared. This plus 3 here is when you distribute this minus, it becomes positive 3. So now that 2x and 2x cancel, and you get negative 5 over 2x minus 8 squared. That's the first derivative. And I like it because it's nice and simple and short. And it can be rewritten as negative 5 2x minus 8 to the negative 2. So now the second derivative is easy. Drop down negative 2 becomes negative 2 times negative 5, positive 10. I'm using chain rule. And then minus 3 because you subtract 1. And then the derivative of the inside is 2.
Professor, did you bring it for the first derivative? It's supposed to be negative 10.
Yeah.
Yes. Negative 10. Time to go home. Is this better?
Yes, it is.
Thank you. So we have 40 over 2x minus 8 cubed. Well, thank you. That saved the day. First derivative test. How about I give you 20 seconds? Go. Okay, so we set the first derivative equal to 0. And we find no solution because negative 10 is not the same as 0. So no solution. Now when we partition, we still have to partition at 4 because that's where the vertical asymptote is. We partition on critical points and vertical asymptotes. You might not have any of them, like last time, but sometimes you have one, sometimes you have both, or multiple asymptotes. That's possible too. Pick 2 test points. Let's pick 0, obviously. And on the other side, you can pick whatever you want. What should you pick on the other side? 5 it is. First derivative computed at 0 is negative 10 over negative 8 squared. That's going to kill the negative, so we have less than 0. We don't care what the value is. We just want to know whether it's positive or negative. When you square a negative number, you get positive, so you have negative divided by positive, and that is going to be negative. The first derivative calculated at the other test point, 5, is negative 10 over, and now you have 10 minus 8 squared, which is what? Also negative, right? We will have negative divided by positive. I don't care what the numbers are because I see that the denominator is squared. If the denominator is squared, it's a positive number. So negative divided by positive is negative. I don't care what the values are. Great, that's the first derivative test. Second derivative test. We take the second derivative, which is 40 over 2x minus 8. Was that cubed? Yes. Equal to 0. And again, 40 is not the same as 0. No inflection points. Okay, fine. But we still get to partition at 4 because the vertical asymptote is preserved from derivative, from function to derivative to the next derivative and so on. So you can take a look at your function, and both derivatives all had the vertical asymptote at 4. So partitions have to be done in this case at 4. Pick 2 numbers. Now you like 5. That's okay. And we find the second derivative of 0, which is going to be 40 over negative 8 cubed. All right, so cubes will preserve that negative because it's negative 8 times negative 8 times negative 8. That's 3 negative 8s. That's odd number of minus signs, which means what? Negative. Fun, no? So concave down because the second derivative on that interval worked out to be negative. The next test point is at 5. That's 40 divided by 2 cubed, which is actually 5. So that's larger than 0, concave up. So we have a concave up and concave down piece. Good. So now we are going to graph the function. With all of the values that we have found so far. We have 3 halves and a 0. So 1, 2, 3, 4. 4 is where my vertical asymptote is. X equals 4. Then we had y equals 1. Horizontal asymptote. we had a point x-intercept at 1.5, so that's the 3/2, and we had another point at 0 and 3/8. 0 and 3/8 is some here. 3/8. Okay, so looking at these two red points, and knowing that the function has to follow asymptotes, there is only one way you can fit the line so that satisfies all of these conditions, and that is you follow this asymptote, then run through these 2 points, and follow the red asymptote. So you follow the blue asymptote to infinity, and then you go through the y-intercept, you go through the x-intercept, and then you have to follow the other asymptote. Now, if you take a look, you have to have a decrease and you have to have concave down. It is concave down, and you have a decrease. Great. Now, the second part is decrease and concave up. So I get to draw two shapes. One is going to go here, the other one is going to go here. Which one do I eliminate? Which one do I keep? Keep the top, eliminate the bottom. Good. Now there is one more thing that tells us that we need to eliminate the bottom one. Can you see what is the other thing that we don't have? Another x-intercept. Exactly. That's very good.
Right.
See this over here? There is another x-intercept here. So if this was the answer, you would be able to compute this x-intercept. But since this is not an answer, there is no other x-intercept. The only x-intercept you have is 3/2. So it has to be the top part. Now you see it's decreasing and it's concave up. So we're all good. So that's what the graph for this function looks like. Now you go to Desmos and you graph it. So the top is 2x minus 3 divided by 2x minus 8. And there it is. You can see the intercept at 1 over here, 1.5, 1.5. You can see your 3/8 over here, which is 0.375. And you see the rest of the, clearly there is a vertical asymptote at 4. So it worked. All right, so what I'm going to do in interest of time, I am going to go through one more example, which is all going to be on a stream and in notes. But since we have about 23 minutes, if you still need to put some finishing touches on your lab so you can hand it in before you leave. If you want to work on labs, you work on labs. If you're paying attention to the problem, pay attention to the problem. If you want to leave, by all means. I mean, that's...
Why not? You can't leave out, you can't leave out there. They might be nesting.
So one more example. You can do something cute or something a little bit more. 45 x plus tangent x. You like that? Now I think they gave us the interval from negative pi over 2 to pi over 2, so that's your domain. You don't have to do number 1. They already gave you the domain at which this thing is going to live at. Again, if you need to do the lab, do the lab. If you want to pay attention to the problem, pay attention to the problem. X-intercept is when y is equal to 0. We get x plus tangent x equal to 0. Now, x plus tangent x equal to 0 is not an equation that you can solve, because it's mixing polynomial function with a transcendental function, the trig function, and they do not mix. There's no algebra that connects them. The only way to solve this function is to graph it, right, which is what we don't know, and then look for intercept with the right 0. So we cannot do this. So I'm just going to put the sad face, and we're going to move on to y-intercept. As I said, if you guys, if you run into a problem that, okay, you're making fun of my here, is this better? Or should I import the Pennywise clown? Right there, drop it right there. There's gonna be someone saying, oh, I don't like clowns. Great, we're gonna now use them on a double. So when x is equal to 0, we get 0 plus tangent 0 equals 2, and we get 0. So we get 0, 0. Hey, this is the y and x intercept at the same time. Great. Vertical asymptote? Yes, yes, yes. Right? X equals negative pi over 2. And x equals positive pi over 2, because tangent has asymptotes at those locations. Horizontal asymptote? None. And slant asymptote? None. Because no polynomials there. Great. We have first derivative, which would be 1 plus secant squared x. 1 plus secant squared x. And the second derivative, what's the derivative of secant? Very good. So the derivative of secant squared is 2 secant times secant x tangent x. So this part over here is the chain rule. You have derivative of secant squared is 2 secant to the first power, and then the derivative of secant from the inside for the chain rule is secant tangent. So the derivative, the second derivative, is actually 2 secant squared x tangent x. So now we have our first derivative test. We say 1 plus secant squared x equal to 0. And you need to solve this equation. What do we do now? Do what?
If you subtract 1, you get secant squared x equals 1.
So if I subtract 1, I get secant squared x equals -1. If I take a square root, it's going to be I.
I1.
So no.
Well, there's probably a trig identity in there. I don't remember.
Oh, that's.
Well, what about we factor it into secant secant x? And we apply the secant x out.
So this is the equation we need to solve. This didn't work. Secant is 1 over cosine, right? So we can try that. 1 plus 1 over cosine squared x equal to 0. Multiply through by cosine squared x to give you cosine squared x plus 1 equal to 0. There's no way that you can get rid of this -1. See, cosine squared x equals -1. So no matter which way you flip this, you always get square root of -1. So no solution. Now, we only had our partitions and endpoints, -π/2 and +π/2 for this. So we can just pick a point. Everything is one partition. So this entire function is either always increasing or always decreasing. Let's find out. We find our first derivative computed at 0, which is 1 plus secant squared of 0. Now, this is 1 plus 1 over cosine of 0 squared, so it's equal to 2. Cosine of 0 is 1, 1 divided by 1 is 1, 1 squared is 1, 1 plus 1 is 2. So 2 is larger than 0, therefore the entire function on this entire domain from -π/2 to π/2 is positive, increasing. So it's increasing. Second derivative test has 2 secant squared x tangent x equal to 0. What do you mean? There is a solution. When you set each one of these equal to 0, you get 2 equal to 0. Well, that has no solution. Then you have secant squared x equal to 0 and tangent x equal to 0. Now we know this one for fact is 0. So we know there is a solution there. Now how about secant squared? Can secant square be 0? Where? No? We did secant of 0, but we didn't calculate. So now if you square root both sides, you get that the secant x is equal to 0, which is 1 over cosine x equal to 0. When you cross multiply, you get 1 equals 0, so no solution there either. So the only one that we have for second derivative test is x equals 0. So we'll have to partition at -π/2, 0, and π/2. And we have to pick our test points. So x use -π/4 and +π/4, as those are easy to compute in tangent. Well, and in secant too. So now we calculate the second derivative at -π/4, which is 2 times secant squared of negative pi over 4 times tangent of negative pi over 4. Now, you can take your calculator and compute this. Fine. Or if you know even and odd functions for trig, you immediately see this is negative. Because secant is 1 over cosine. Cosine is even function. So cosine of the even or odd over here is always going to give us positive value. So number 2 is always positive. Secant, or actually you don't care what it is. It's squared. What am I talking about? It's squared. The term is squared. Whether it's positive or negative, it's squared, so it's positive. And then here the tangent is the tangent is odd function, so the negative jumps in front, so that's going to be negative, so the whole thing is less than 0, meaning concave down on this piece. And if we have positive pi over 4, we have the same analysis. And that's going to be concave up. Because all of the terms are positive.
Oh.
And then we draw the graph. So let's set negative pi over 2 and positive pi over 2.
I missed out on some of the class here. What
We have a 0, 0.
What does CV and CU represent?
That's yesterday's class. It was concave up and concave down from the second derivative test.
I don't think I was here for that yesterday. Was that at the beginning before I arrived?
Maybe, I'm not sure.
Okay. I'll look into it. Oh.
So it must look like this, right? It goes through 0, 0, origin. The piece on the left has to be increasing and it has to be concave down. You see that this is increasing and it's concave down because it spills water. On the other side has to be increasing and concave up. That's increasing and concave up. So this is the only way this can work. So this is x plus tangent x. And if you take a look at the Desmos graph as well, there it is.
Wow.
So the green, just we're looking only at the middle green here, and it goes through 0, 0. It has an inflection point there. You see this one is concave down and increasing, this one is concave up and increasing.
Yeah, it's enough.
And over here, the asymptote, right, is pi over 2, which is like about 1.57. So that's what we have. For graphing functions, we did not learn any new concepts. We only took the old concepts you guys know from before and put them on a pile, and you just compute all of those to come up with the graph. So domain, x and y intercepts, vertical asymptote, horizontal asymptote, slant asymptote, first and second derivative, and then first, second derivative tests. And if we need extra stuff, symmetry and behavior, additional points, so we can finally graph stuff. So I'm going to post these lectures, so you can, guys, if you didn't get to write this stuff, you can have it. And then on Monday, we'll try to finish the chapter on Monday and Tuesday next week. Maybe also into Wednesday. And then after that, we have 5 sections of chapter 5 to complete the course. Exactly. So that's what we have.